This is the B-1 Lancer. It carries more weapons than any U.S. bomber and still hits Mach 1 at 200 feet. But the system that makes both possible hides inside the wings, and most people have never heard of it. Get it wrong, and this aircraft cannot fly at all. It starts with a problem no other bomber has ever had to solve. Most aircraft commit to one wing shape and accept whatever trade-offs come with it. Fighters take short, swept wings for supersonic speed. Transports take long, straight wings for lift and fuel economy. The B-1 Lancer needs both, on the same airframe during the same mission, sometimes within minutes of each other. It has to lift 477,000 pounds off a standard runway, cruise efficiently across an ocean, and compress itself into a low-altitude supersonic penetrator before any radar operator knows it is there. A no-fixed-wing geometry does all three. The answer was to build a wing that physically changes its own shape in flight. The B-1 uses a variable sweep wing. At 15 degrees, the wings extend fully forward, spanning 137 feet tip to tip, roughly the width of a 12-story building laid flat on its side. In this position, the aircraft generates maximum lift. Without that span, 477,000 pounds never leaves the runway. At 67.5 degrees, the wings sweep back against the fuselage and the span contracts to 79 feet. The aircraft becomes a fundamentally different shape, narrower and denser, built for Mach 1.25. Pilots can set any angle between those two extremes. The wing responds to a cockpit switch. Sweep takes approximately 30 seconds to complete. Too fast under high aerodynamic load and the pivot bearings fracture, leaving the wing locked at whatever angle it held when the mechanism failed. Too slow entering the high-speed regime and aerodynamic oscillation builds a vibration pattern that propagates through the entire airframe until something reaches its structural limit. But the wing is only half the equation. The structure holding it in place is what nobody talks about. Inside the B-1's fuselage, buried where no technician on the ramp can see it, sits what engineers call the carry-through box. It is the aircraft's structural spine. Both wings pivot on this single component. Every force the wing generates in flight, lift, drag, G-load during combat maneuvering, passes through this box before reaching any other part of the airframe. It is machined from titanium. Fully assembled, it weighs approximately 14,000 pounds, roughly the same as 3 fully loaded pickup trucks packed into a space about the length of a compact car at the center of the fuselage. If it fails in flight, the wings depart the aircraft in under a second. There is no recovering from that. The machined surfaces are held to tolerances measured in thousandths of an inch. Too loose and micro movement under G-load initiates fatigue cracking at the pivot points, damage that compounds with every sortie until the joint fails outright. Too tight and thermal expansion at cruise altitude causes the pivot mechanism to bind, locking the wings at their current position and removing the crew's ability to change configuration mid-mission. The hydraulic actuators that command the sweep live at the pivot points on each side of the box. Each one generates enough force to move a loaded wing against 500 miles per hour airflow. In physical terms, the output of each actuator matches the rated lift capacity of a large industrial construction crane, applied not vertically but in a controlled arc, metered continuously by the flight control computer. The system moves a structure weighing tens of thousands of pounds as if it weighs nothing. It just works. And that structure has to survive something most aircraft are never asked to experience. The hydraulic pressure rises. The wing begins to move. The leading edge travels visibly, the pivot fitting cycling through load as the angle increases. Inside the cockpit, an instrument needle tracks the sweep position in real time. The pilot calls each major increment on intercom: 15 degrees, 30, 50. And the aircraft's handling character changes at each position, less stable laterally, sharper in pitch response. The crew feels this shift through their seats and the controls beneath their hands. At 67.5 degrees, the motion stops. The sweep took 28 seconds. The aircraft that departed the runway this morning and the aircraft now approaching the target corridor are, aerodynamically, two different machines. The B-1 was built to penetrate defended airspace at low altitude, not descend through it briefly on approach, not transit it on the way to a higher corridor. Penetrate it, sustained, at speeds above Mach 1 in weather, over terrain that rises and falls faster than any human pilot can react to. At that combination of speed and altitude, dynamic pressure on the airframe is extreme. The forces are high enough to flex the fuselage measurably. Engineers did not classify this as a design flaw. They calculated it into the load analysis as designed behavior from the beginning. Every hour of low-level, high-speed flight consumes structural life at roughly 3 times the rate of the same hour spent at altitude. The B-1 fleet has a finite number of those hours across its entire airframe. When they are consumed, the aircraft are retired. Calendar age does not make that determination. The airframe log does. This is why mission planning for low-level profiles is not purely tactical. It is actuarial. There is a system inside the B-1 that does something no human pilot physically can. At 200 feet and Mach 0.85, terrain rises faster than any human can respond to it. A ridgeline at that speed and altitude gives the crew less than 2 seconds before impact. An average human reaction time from visual stimulus to control input runs approximately 0.8 seconds, and converting that input into actual aircraft pitch change requires additional time. At these speeds, the combined delay is fatal. The answer is the terrain-following radar, a system that reads the ground ahead, calculates the required pitch correction, and commands the autopilot to execute it in approximately 0.3 seconds before the crew has consciously registered the obstacle. That gap between 0.8 and 0.3 seconds is the difference between a completed mission and a smoking hole in the terrain below. The system reads ahead to 12 miles, giving the aircraft enough lead time to calculate the minimum safe path through whatever lies ahead. Before entering the low-level corridor, the crew selects ride quality. Smooth means the autopilot accepts a higher average altitude in exchange for predictable G loading. Hard means it tracks the terrain floor as tightly as physics allow, pulling whatever G is required to clear each obstacle with no additional buffer. Most crews choose hard. Nobody chooses it because it is comfortable. The wing moves, the aircraft sweeps, and then the real problem begins, because a bomber that can change its own shape is still useless if it cannot survive the environment it is about to fly into. The terrain-following radar is not a navigation aid. It is what keeps the crew alive during the parts of the mission no human can fly manually. The system uses a forward-looking beam to build a continuous terrain profile of the ground ahead, updating that picture many times per second. It calculates the minimum safe altitude path in real time and commands the autopilot to fly it without waiting for crew input. At Mach 0.85, the 12-mile read range ahead represents approximately 85 seconds of flight time. Barely enough margin to plan around, but more than the crew would have without it. Before entering the low-level corridor, the crew selects ride quality, and that selection holds for the duration of the leg. Smooth means the autopilot responds gradually, accepting a slightly higher average altitude in exchange for more predictable G loading and better crew endurance through long legs. Hard means the system tracks the terrain as tightly as physics permit. Too sensitive on the hard setting, and the autopilot pulls 4 or more Gs over a sharp terrain feature, is spiking past the crew's G tolerance limit and causing them to lose consciousness at the most critical phase of the mission. Too conservative, and the aircraft drifts above its designated altitude floor, rising into exactly the radar coverage that the entire low-level ingress was designed to avoid. The aircraft is at 200 feet. Below the cockpit, terrain rushes past in a compressed blur. Faster than freeway traffic appears from a low-flying helicopter and far more immediate. The autopilot pushes the nose up 0.3 seconds before anyone in the cockpit sees the ridgeline ahead. The aircraft bucks hard. Warning tones fill the helmets. The crew's hands rest on the controls without gripping them, ready to override, feeling the correction arrive before they understand what triggered it. The ridge disappears below. The aircraft levels. In the rear cockpit, the defensive systems officer is already scanning the next line on the threat display. Nobody has time to note the terrain that just passed. But surviving the terrain is not the only thing the low-level environment is consuming. At Mach 0.85 and 200 feet, dynamic pressure on the B-1's airframe is roughly equivalent to the structural load of a Category 5 hurricane, striking every exposed surface simultaneously, sustained for the entire duration of the low-level leg. The fuselage flexes under this load. The carry-through box cycles through stress with every autopilot correction. Every G pulled to clear terrain is a fatigue cycle. Engineers calculate that high-speed, low-level flight consumes airframe structural life at approximately 3 times the rate of the same time spent at cruise altitude. Several B-1 airframes have been retired ahead of their projected maintenance schedules, specifically because accumulated low-level training hours exhausted their fatigue life before the calendar anticipated. The operational G limit for the low-level mission profile is 2.0 G, exceeded in the moment during a hard TFR correction or a combat maneuver, and the aircraft is operating outside its structural envelope. At Mach 0.85 and 200 feet, operating outside the envelope is where structural failures begin. The B-1's 4 GEF-101-GE-102 turbofan engines each produce up to 30,780 pounds of thrust with afterburner. With afterburner active, the exhaust plume creates an infrared signature detectable by IR-guided systems at ranges approaching 30 miles, roughly the distance from a city center to the outer edge of its surrounding metropolitan area. In a low-altitude penetration profile, a signature that size is not a tactical limitation. It is a targeting solution for anyone looking. Afterburner use at low level is confined to the dash to weapons release airspeed and executed in brief, precisely timed bursts. Too frequent, and the aircraft has broadcast its position to every IR sensor in the threat envelope during the mission's most vulnerable phase. Too short, and the aircraft arrives at the release point below the required airspeed, which shifts the weapon's ballistic solution and moves the planned impact point outside acceptable accuracy parameters. The afterburner lights. The kick arrives before the sound registers in the helmets. A physical push, the seat pressing up and back simultaneously. The fuel flow gauges spike. The vibration note changes. As a lower resonance added to the existing engine noise. On the rear seat threat display, the infrared signature assessment updates in real time. The bloom has expanded significantly. Everyone in the aircraft knows exactly what that means. The burn lasts seconds. The throttles come back. The aircraft is at release speed. Every low-level sortie is a trade. Performance now, airframe life later. 4 people sit in an aircraft sophisticated enough to fly significant portions of its attack profile on autopilot. Here is why 4 humans are still not enough. The pilot and co-pilot manage the aircraft through each flight phase. The mission's actual complexity lives in the seats behind them. The offensive systems officer manages the 3 internal weapons bays, coordinates targeting data, and sequences weapon release across the attack profile. The defensive systems officer manages the AN/ALQ 161 electronic countermeasures system, which automatically detects, classifies, and begins responding to radar threats in under 2 seconds, compared to the 8 to 12 seconds a human operator requires for the same assessment. But the system cannot make the decisions the DSO makes. Which threats to prioritize when 4 emitters are active from different bearings. Which countermeasures to suppress in order to preserve the aircraft's own radar picture, whether to jam an emitter or maneuver away from it. At 200 feet with multiple radar systems painting the fuselage, every one of those decisions happens in seconds and cannot be reversed. Nobody applies for the DSO position because the working conditions are favorable. But all of that is preparation. What happens when the B-1's weapons bay doors open at Mach 1.25 is something the engineers spent years getting right, and several destructive test failures getting wrong before they did. The B-1 carries all weapons internally across 3 bays. There are no external hardpoints during penetration missions. External weapons at supersonic speed create drag that degrades the entire mission profile, and radar returns that negate the low-altitude stealth concept completely. Everything goes inside or it does not fly. The forward bay handles smaller munitions. The 2 aft bays share a rotary launcher, a cylindrical rack that rotates to position each weapon for release, similar in concept to the revolving cylinder of a handgun scaled up to hold bombs that each weigh a ton. At cruise altitude, the mechanism functions smoothly. At Mach 1 and 200 feet, the vibration environment inside the fuselage is severe enough to tighten the launcher's operational tolerances significantly. A weapon that shifts on its rack by more than the width of a finger can fail to maintain its electrical connection with the aircraft's stores management system. Without that connection, it receives no targeting data. It falls as unguided ballistic weight, missing the intended target by miles. The weapons bay doors each weigh approximately as much as a mid-size SUV. They open on precision hinges that must be aligned within tight tolerances, or they create localized aerodynamic disruption that compounds the existing airflow problem at the open bay. At Mach 1.25, the doors open. The airframe shudders immediately, a low, resonant vibration that transmits through every seat and every surface in the cockpit. The ambient noise level inside rises sharply. Airflow through the open bay cavity at 600 miles per hour exerts continuous pressure against each weapon's mounting hardware. The rotary launcher holds position against that load. The bay stays open for approximately 4 seconds, long enough for the weapon to be positioned and released, short enough to limit the radar exposure window. Too long, and the aircraft's radar cross-section expands by an order of magnitude, making it detectable to every radar system in the threat envelope for exactly as long as those doors remain open. Too short, and the weapon does not achieve clean separation, contacting the bay structure on exit and converting a precision-guided munition into an unguided projectile. The doors close. The vibration stops. The aircraft is a stealth platform again, and the defensive system running in the background has not paused once during any of this. The AN/ALQ-161 classifies a new emitter and begins responding before the DSO has completed a manual assessment of the same signal. The DSO's role is not to be faster than the system. It is to be smarter, overriding the automated response when the tactical situation requires it, managing 4 simultaneous threat environments, and making jamming versus evasion decisions that the threat library cannot resolve. None of this stops during the weapons release window. The DSO works through the bay door open sequence without interruption. There is nothing in the mission that pauses for anyone to think. The coordinates loaded into the weapon before takeoff are not the coordinates it will use at the moment of release. The aircraft's mission computer retains current targeting data and can receive retargeting instructions via secure data link throughout the flight. The offensive systems officer can update the weapon's target during the attack run itself. The weapon does not know its final destination until the umbilical transmits that data during the release sequence. This means the B-1 can strike a target that did not exist as a priority when it departed the runway. A relocated asset, a time-sensitive target that emerged en route, a close air support request received while the aircraft was already in the target corridor. The release sequence happens in fractions of a second. The umbilical transmits the final targeting package: GPS coordinates to 10 decimal places, wind data at multiple altitudes, barometric pressure, planned impact angle. The weapon's computer processes this in milliseconds and runs diagnostic checks on every subsystem. The suspension fittings open, pneumatic ejectors fire, pushing the weapon out of the bay against 600 miles per hour of relative airflow. Too little ejection force, and the weapon contacts the bay edge as the aircraft passes over it. Too much, and it tumbles immediately on exit, the fins unable to stabilize, which makes the guidance system irrelevant regardless of how accurately the coordinates were loaded. The margin between those two outcomes is precisely calibrated for each weapon type. The weapon clears the bay. The fins deploy. The GPS receiver begins acquiring satellites. The aircraft does not slow down. The aircraft does not watch. It has already begun its egress turn. The offensive systems officer logs the release time and weapon status. The mission computer records airspeed, altitude, heading, and G-load at the exact moment the umbilical disconnected. This data feeds into post-mission analysis. If the weapon misses, the log identifies which release variable was outside tolerance. If it hits, the same numbers are archived as a reference standard. Nothing about the release is undocumented. Release altitude determines time of flight. Release airspeed determines the weapon's initial trajectory. A deviation of 300 feet in altitude or 5 knots in airspeed at the moment of release moves the impact point outside the weapon's stated accuracy specification. The crew has one opportunity to deliver each weapon inside those parameters. The approach was either correct or it was not. There is no correcting a weapon that has already left the bay. By the time the weapon reaches terminal phase and makes its final guidance correction, the B-1 is miles away and the bay doors are closed. The radar cross-section has returned to baseline. If there is a second target, the rotary launcher has already positioned the next weapon. The fins adjust. The GPS solution refines. The final correction comes a fraction of a second before impact. The B-1 is already gone. B-1 is already gone. B-1 is already gone.